Good morning, everyone. I hope you're all having a fantastic day. We are going to be talking about the most basic form of linear regression today, which is known as simple linear regression, and it's looking at the relationship between a response variable and a single predictor variable. When we're talking about the relationship between variables, there are two different kinds of relationships that we might discuss. The first is called a functional relation, and a functional relation is between two variables can be expressed using a mathematical formula. So if we let x denote something called an independent variable and y denote something called a dependent variable, then the functional relationship between x and y is that y is equal to f of x. In other words, the dependent variable is equal to some function of the independent variable. The thing about a functional relationship is that the relationship is exact. If you know the value of the independent variable and you know the function under consideration f, then you know the exact value of y. There's absolutely no uncertainty. As you might expect, that kind of relationship is not really found in the real world. We don't get exact relationships like that. So instead, we're going to talk about how to examine statistical relationships. And in a statistical relationship, we're still going to have an x and a y, but the x can be described more broadly as the independent, explanatory, or predictor variable. I'll typically go between explanatory and predictor variable in terms of what I actually call it. And y is now called the response, outcome, or dependent variable. And I'll typically favor calling it the response variable, though I could use any of those terms interchangeably. So the statistical relationship between the predictor and response variable is that the response y is equal to f of x, so some functional relationship, plus error. So the main idea is that we have some model, some functional relationship, but then even if we know the value of x, we know our function f, there's some additional uncertainty that we can't quite explain, and that is what's captured in this error right here. So if we looked at some graphs of a functional relation versus a statistical relation, we might see something like this. So for our functional relationship, we see that the relationship between x and y is exact. In this case, it's a perfectly straight line. It doesn't necessarily have to be. It could be some sort of curve if we wanted, but it's a straight line for simplicity here. And the main picture here is that if we have this line right here, for any value of x, we can know exactly the value of y that we're going to get. So this relationship is exact. If we look on the right-hand panel here, in the statistical relation, we see a somewhat similar relationship. And actually, you can see the numbers are pretty similar here. But the difference is that whereas if we know x and we know f, we can get an exact relationship on the left-hand side, it's not going to be exact right here. So it's going to be close to the functional relation, but there's some additional error for each of the observations that we can't quite explain. So what is the most basic form of statistical relationship that we can talk about? And one of the most basics is the simple linear regression model. So we have a few different terms that need to be identified here. So y sub I is going to be the value of the response variable for the ith observation. So we imagine that we have n pieces of information, and for each piece of information there's going to be a y, which is the response for that observation. There's also going to be x, which is the value of the predictor variable for the ith observation. Beta naught and beta 1 are going to be regression coefficients or parameters. These are unknown constants related to the distribution of the data. So we don't know them, we're going to have to estimate them, but they're in fact unknown constants that we want to estimate. And then we'll let epsilon I denote the random error term for the ith observation, and the errors, the assumptions that we make about the errors is that on average the value is equal to 0, that their variance is equal to sigma squared, and that any two errors are going to be uncorrelated. So these are pretty standard assumptions that we make for a simple linear regression model. And using those terms, in the simple linear regression model, it says that the ith response is equal to beta naught plus beta 1 xi plus epsilon I. In other words, it says that the ith response is based on some linear function of x, that's what this beta naught plus beta 1 xi part is, plus some random error that we can't capture completely. This model is called simple because it has only one predictor variable. As we'll see in later chapters, we can have more than one predictor variable, in which case we're doing multiple linear regression. We're doing multiple regression. So that's why the model is called simple, but then as I mentioned, it's a simple linear regression model. And the model is called linear because it's linear in the regression coefficients. Those are the beta terms. which means that the parameters do not appear in an exponent or as a product or quotients of each other, which essentially means that we can write our regression model as some sort of linear combination. So an example of a nonlinear model would be beta naught plus e to the exponential function to the beta 1 power times x. In this case, the parameter here appears in the exponent, e to the beta 1 power, and so that would be an example of a nonlinear model. However, or I guess related to the simple linear regression model is the first order linear model, which means that the regression relationship is linear in both the predictors and the regression coefficients. So a first order linear model, to write it in the multiple regression context, would be something like y sub I equals beta naught plus beta 1 xi 1 plus beta 2 xi2 plus epsilon I. Okay, so in this case, the model is linear in both the regression parameters as well as the predictor variables. And so that would be a first order linear regression model. However, that's going to be a little bit complex for what we actually want to do right now, so let's not worry about that at this time. So a few things to note about our simple linear regression model. The first is that the ith response is the sum of a functional relationship, beta naught plus beta 1 xi, so this relationship is exact, plus the random error term epsilon I. You should also note that the mean response for the ith observation is beta naught plus beta 1 xi. So the response y sub I comes from a distribution that has mean, or expected value, equal to beta naught plus beta 1 xi. And this inner part, this kernel, is called the regression function. And the regression function of our model is going to be beta naught plus beta 1x. So this is the functional relationship, the functional relation part of our simple linear regression model. The epsilon I, the error term that we've already talked about, is going to be the discrepancy between the regression function, which we have right here, and the observed response. So the error term is really the difference between the functional relation and the statistical relation. Another thing, a few things that you should be aware of, or another couple of things you should be aware of, is that since the errors have constant variance, so will the responses at each level of x, which means that when you're looking at the errors in a plot, for example, the variability around your regression line should be pretty much constant. Additionally, since the error terms are uncorrelated, because the epsilon i's are uncorrelated, so are the responses. So there's not going to be any correlation between the different responses. So let's try to do a practical example of this. So a consultant for an electrical distributor is studying the relationship between the number of bids requested by construction contractors for basic lighting equipment during a week and the time required to prepare the bids. So suppose the regression function, or the functional relation, is e sub y is equal, or e sub y is equal to 9.5 plus 2.1x. So we have the functional or regression relationship right here. And at each observed value of x, we observe a value, a response, drawn from a distribution centered at this particular mean right here. So this graph is trying to indicate exactly what we're talking about. So this is the x-axis, this is the y-axis. We're looking at the number of hours to prepare the bid versus the number of bids prepared. And you can see this straight line right here is the functional relation, the regression relation, the regression function equal to 9.5 plus 2.1x. So that's a straight line. So this is the average response, the average number of hours it takes to prepare a bid versus the number of bids that have to actually be prepared. And what we imagine is that for each x, so let's say that we have an x value of 25. For each value of x, there's going to be some distribution, which we'll typically assume is going to be normal, but we're not assuming that quite yet. But there's some distribution at each value of x for the response. And so for that particular value of x, the distribution is centered here at 9.5 plus 2.1x. And we draw a random error from this distribution and we add it to the functional relation, to the regression function. And that gives us our observation for the observed data value. So actually this probably is a better example right here. So if we look at x equal to 45 and we plug it into our regression function 9.5 plus 2.1x, we get a value of 104. So this is the mean response when the number of bids prepared is 45. And then being centered at that mean response, we draw an observation from this error distribution, and we'll assume that the error for that particular observation is equal to 4. So we add 4 to our regression function, and we get 108. So our x value in this case is 45. The mean response when x is equal to 45 is 104, but the actual response we observe is 108 because of the random error. So how do we understand these different parameters that are in our model? Well, the intercept term beta naught represents the mean response when x is equal to 0. So in this particular case, in this particular context, what it means is that the average number of preparation hours, beta naught is going to be the average number of preparation hours when the number of bids prepared is 0. However, I will say that oftentimes, even though that's the mathematical interpretation of beta naught, oftentimes it's not going to make any sense whatsoever. So it might be a negative number or a positive number when the predictor variable is equal to 0, which may not make sense at all in practice. And typically that happens when the value x equal to 0 is outside the range of the observed values of x. So in other words, when you're extrapolating outside the range of observed data, oftentimes the intercept term is not going to make practical sense, even though it makes mathematical sense. The beta 1 regression parameter represents the mean or average amount of change when x increases by 1 unit. So this is going back to the days of algebra in maybe 8th grade or 9th grade or 10th grade, depending on when you took algebra. And this is the idea of rise over run. So when x increases by 1 unit, how much does the response change on average? And in this particular context, beta 1 represents the change in the mean number of hours of preparation when the number of bids increases by 1 unit. So in this case, the average number of hours of preparation increases by 2.1 hours when the number of bids increases by 1. If you remember, we actually know the exact regression function in this case. So beta naught is equal to 9.5, beta 1 is equal to 2.1. And so in this particular context, the average number of hours of preparation increases by 2.1 hours when the number of bids increases by 1. In other words, if a company asks for an additional bid, it's going to take the owner of the company about 2.1 additional hours to finish preparing the bids for them. So this right here is a visual description of the interpretation that we just discussed. So you see here the number of bids prepared goes from 0 out to x of about 40, and the value of beta naught is 9.5. So when x is equal to 0, the value of the average response is going to be 9.5. And we can interpret it in this context that if there are no bids to be prepared, it still takes 9.5 hours to prepare a workup for the contractor, which of course doesn't make practical sense, right? If they're not making any bids, then it takes exactly 0 time. But that's outside the range of the observed data, which is why it doesn't make sense in this particular context. When we're looking at beta 1, okay, so we're going to zoom in here on this little section. What it's saying is that for each additional unit increase in x, so when we move along the x-axis in the positive direction, the average change in y is going to be 2.1. So y increases by about 2.1 units for each additional unit increase in x. So those are the interpretations of beta naught and beta 1. So we should make a brief note about the different kinds of data that we work with when doing regression. So the two main types, of course, are observational data and experimental data. Observational data is data obtained from non-experimental studies in which the predictor variables are not controlled. So we simply observe the predictor variable and the response. We're not trying to control anything. This is common in social data, for example, so when we're actually interviewing people out on the streets or something like that. The downside of using observational data is that you cannot make cause and effect relationships for this type of data because the change you see, the impact you see, might be explained by some variable that we didn't measure or we didn't control. On the other hand, for experimental data, the data is obtained through some sort of experiment, which means essentially that the explanatory or predictor variable was controlled through random assignment to the experimental unit. So we didn't simply observe the predictor variable or explanatory variable. We actually dictated the value it was going to have in some way, whether we assigned it randomly or not. And the various combinations of the explanatory variables that each experimental unit can receive are called treatments. So if we only have a single explanatory variable, so maybe it's different kinds of cough medicine, for example, each kind of cough medicine would be a different treatment. And the most basic kind of experiment is the completely randomized design where each of the different treatments are randomly assigned to the experimental units. And we won't talk a lot about experiments until about the last 2 weeks of the semester or so. But experimental design is a very important aspect of regression and statistics. So up to this point, we've introduced the simple linear regression model. We've talked about the parameters, the model components, but we haven't talked about how in the world we actually find or estimate the unknown parameters. So let's motivate this with an example. So the Ch01 company manufactures refrigeration equipment as well as many replacement parts. The company would like to determine the optimum lot size for producing a replacement part. A key component of this is the number of labor hours versus the lot size. A sample of 25 runs were collected over a 6-month period of stable production runs. The question is, how can we estimate the regression function for this data set? So this is actually a problem that you might see something similar to in real life. So we have a company, they make widgets, and they want to know essentially how many widgets they should make in a certain period. And so what they're going to do is they're going to collect data, and then they're going to try to determine the optimum amount of hours that it takes. So we have a plot here of the observations. So we have the lot size that were produced and the number of work hours it took to produce each of those lots. And the company wants to optimize this function in some way. Maybe it's, actually I really don't know what they want to do, I'll be honest. But there's something about this function that they want to know. Specifically, they want to know the average relationship between lot size and work hours, and then they'll use that information in some way that will benefit the company. And there are lots of different ways actually for estimating the regression parameters. The method that we are going to use, and the most common method in regression, is called the method of least squares. And I'll explain the name here shortly. It's pretty descriptive actually. So we're going to use the least squares approach to estimate the regression function. So let's suppose that we observe a sample of n observations, x1, y1, x2, y2, up to x and yn. Okay, so each of these is an observation. So these are not, each piece of so this x1, y1 describes a single observation. We have an x measurement and a y measurement for the first observation. We have an x measurement and a y measurement for the second observation, and so on. And the reason it's called the least squares approach to estimation is because we choose the regression parameters beta naught and beta 1 by finding the values of beta naught and beta 1 that minimize the least squares criterion, which in this case is we take each of the responses, we subtract off the regression function evaluated at each of the x values, and we square that difference, and then we sum over all the observations. So really what this is doing is this is the sum of the squared deviations from each response. So just to draw a picture of what we're talking about, we had some data. There are many possible lines that we could fit. We could fit that line, we could fit that line, we could fit this line. The question is, which of those lines best fits the data? And so what we're basically going to do, just to make this simple, we'll have 3 observations here. We're going to try to find the line that minimizes the squared vertical distance between each response and the associated estimated regression function. So we choose values of beta naught and beta 1, and that gives us this line right here. And we choose the values of beta naught and beta 1 so that the square distances are going to be minimized. So we have this criterion, this function that we're trying to minimize, and we're going to choose as our estimates of beta naught and beta 1 the values that minimize this function. And the question is, how in the world do we determine those values? And if I just told you that I had a function, I wanted to minimize it or maximize it, the natural approach, if you've taken calculus, of course, is to take the function, or to get the function to take the derivative with respect to the variables of interest, set them equal to 0, and then solve for the unknown parameters. And so that's exactly what we're going to do. So let's derive the least squares estimators. So as I mentioned here, so we have our least squares error criterion. So let's do this. So our least squares error criterion is the sum of the squared deviations. So we have our regression function here. We take the square deviation between the regression function and the observed responses, and we square that difference. And we want to minimize this function with respect to beta naught and beta 1. So the first thing that we'll do here is we will take the derivative of this function with respect to beta naught. Oops. And when we take the derivative, we get the sum of y sub I minus beta naught minus beta 1 xi, and we set that equal to 0. Now what we're going to do is we're going to expand this function out, so we get the sum of the y's minus in beta naught, because we're going to take beta naught and sum it n times, minus beta 1 times the sum of the x's equals 0. And we're solving for beta naught here. So what we get is in beta naught is equal to the sum of the y's minus beta 1 times the sum of the x's. And if we divide both sides by n, we get beta naught is equal to y bar, the sample mean, so the sum of the y's over n, minus beta 1 x bar. And so this is the value of beta naught that's going to minimize the least squares error criterion Q. So we've solved for beta naught, and now, but as we noticed, this involves the other unknown regression parameter beta 1. So we better solve for beta 1 in order to determine our estimator for beta naught. So in order to find the optimal value of beta 1, we take the partial derivative of the least squares error criterion with respect to beta 1. And when we do that, and we'll set that equal to 0, when we do that, what we get is, actually I just realized there's a slight typo here. It doesn't make a difference in the end, but when I take the derivative here, this actually should be a minus 2. Of course, when I divide out the minus 2, it goes away. It doesn't really affect the optimal value of beta naught. But I wanted to correct that while it was on my mind. So to take the partial derivative of q with respect to beta naught, we get minus 2 times the sum of x sub I times y sub I minus beta naught minus beta 1 xi. We set that equal to 0. So we obtain that using the good old-fashioned chain rule that we learned in calculus. We can, of course, divide this negative 2 out, and we'll just expand everything out. So we get the sum of x sub I, y sub I, minus beta naught times the sum of the x's minus beta 1 times the sum of xi squared equals 0. And we notice that this equation right here has beta naught in it, but we've already solved for the optimal value of beta naught, so we're going to plug that in. So this is equal to the sum of x sub I, y sub I, minus y bar minus beta 1 x bar times the sum of the x's minus beta 1, the sum of xi squared equals 0, and that's by substitution. So we simply use the fact that we knew that the optimal value of beta naught was y bar minus beta 1 x bar. We substituted that into our equation under consideration right here. So I'm going to continue to simplify this. So we get the sum of x sub I, y sub I, and the sample mean y bar is simply the sum of the y's multiplied by 1 over n, 1 over the sample size, plus beta 1 times 1 over n times the sum of the x's. So that's the first part there. Oops, and actually I just realized there's a, I'm going to correct this here. So we need to expand this product out. So we're going to get y bar times the sum of the x's, which is the same thing as 1 over n the sum of the y's times the sum of the x's, minus beta 1 times 1 over n the sum of x of I squared, minus beta 1 times the sum of x of I squared equals 0. So continuing on with this equation, what we're going to want to do is we're going to group everything by beta 1 and then factor out the remaining material. So we get the sum of x sub I, y sub I, minus 1 over n, the sum of x sub I times the sum of y sub I, equals beta 1 times the sum of x sub I squared minus, this should be a plus up here, minus 1 over n, the sum of x sub I quantity squared. Okay, so really there's just some messy algebra that we had to deal with. And once we do that, then we simply solve for beta 1. We see that beta 1 is equal to the sum of x sub I, y sub I, minus 1 over n, the sum of x sub I quantity times the sum of y sub I, divided by the sum of x sub I squared minus 1 over n times the sum of the x's quantity squared. So that's the optimal value of beta 1. And so what we've shown now is that the optimal value of beta 1 is y bar minus beta 1 x bar. And since these are going to be estimators, oftentimes the way that we denote an estimator in statistics is using a hat. So the estimator of beta naught is going to be beta naught hat, which is y bar minus beta 1 hat x bar. And beta 1 hat, the optimal value of beta 1, is going to be the sum of x sub I, y sub I, minus 1 over n, the sum of the x's quantity times the sum of the y's, divided by the sum of the square of the x's, minus 1 over n times the sum of the x's squared. And this can be re-expressed as the sum of xi minus x bar times y sub I minus y bar divided by the sum of xi minus x bar squared. So I'm not going to derive this last little bit right here, but you can in fact do it. And so those are the least squares estimators of beta naught and beta 1. So those are the values that you want to use if you want to find the values of beta naught and beta 1 that minimize the least squares error criterion. So let's just jump down a little bit. All right. So the least squares estimator of beta 1 is beta 1 hat, which is equal to one of these two formulas right here. You can actually see that this is actually a third expression that you can obtain. This is simply by multiplying the numerator and denominator of the derivation I made by n, or by 1 actually. So if you multiply by n over n, then you can re-express the least squares estimator for beta 1 using this formula right here. And this is the other formula that I've already provided. And then this is the formula for beta naught hat that we've already looked at. And the Gauss-Markov, so these are the least squares estimators. So regardless of the distribution of the data, these are the values of beta naught and beta 1 that are going to minimize the least squares error criterion. But we also have something called the Gauss-Markov theorem, which states that under the conditions given above, so under the assumptions that we've already made, specifically on the errors, the least squares estimators of beta naught and beta 1 are unbiased and have minimum variance among all unbiased linear estimators. In other words, they're MVUs, using the standard shorthand for minimum variance unbiased estimators. In other words, among all unbiased estimators, these are going to be the estimators of beta naught and beta 1 that provide you with the smallest variance. So at least according to some criterion, these are going to be the best estimators you can possibly find. So one thing I should point out, and make this very clear, is that the book is going to use slightly different notation at times than the notation that I use. So instead of using beta naught hat and beta 1 hat, the book actually uses lowercase b naught and lowercase b1. I don't really like that notation because this is a notation that's actually particular to this book, not to what's used in general. So in most statistics books, in fact the standard statistical practice, is that when you are denoting an estimator of a parameter, you simply put the hat symbol above the parameter, and that denotes the estimator. And so in order to stick with the typical convention, I'm going to use beta naught hat and beta 1 hat when I do my lecture notes, when I work out examples, as opposed to using the book's notation of b naught and beta 1, where the two things are equivalent. So hopefully that won't confuse you, but I wanted to make you aware of the slight distinction in notation. So let's talk about the Toluca example. So we want to estimate beta naught and beta 1. We want to find the least squares estimators of beta naught and beta 1. And I'll tell you from R that the values are 62.37 and 3.57, which means that the estimated regression function y hat is going to be beta naught hat plus beta 1 hat x, which is equal to 62.37 plus 3.57x. So we know that our regression function is y equals beta naught plus beta 1x, and thus the estimated regression function is simply the regression function with the parameters replaced by their estimators. And just to interpret what this actually means, we'll first interpret beta naught hat. So we estimate that for a lot size of 0, it will take 62.37 work hours on average to produce that lot. Of course, this makes absolutely no sense whatsoever, because if the lot size were 0, the number of hours it would take to produce that lot would of course be 0 hours. However, that is the correct mathematical interpretation of the estimated beta naught parameter. Additionally, we'll talk about the interpretation of beta 1 hat. So the estimated slope parameter, and the interpretation of that is that we estimate that for each additional unit produced in a lot, it's going to take about 3.57 hours on average to produce the lot of that size. So if you increase lot size by 1, you can expect about 3.57 additional hours on average for the job to be completed. Of course, you're probably wondering how in the world I got these numbers. And so we're going to look at R. I'm not expecting you to really be able to do this yet. I'm just going to show you how I got it, and perhaps this will motivate you to play around a little bit with R on your own. So here is the chapter01.r file, which should be available on Blackboard for you to use. And I'll walk you through the analysis that I've done just to make things easy on you. So we have this Toluca data. The first thing that we need to do is we need to read this data into R. We have to be able to access this data. And the data for the book is easily available online. If you just do a Google search, you should find it pretty easily. And the data for this particular example is available in chapter 01 TA01.text. And so in order to read the data into R, the most convenient function to use is the read.table function. So what I'm going to do is I'm going to use the read.table function. I'm going to specify the file I want to read in, and then R is going to read it into an object that I named Toluca. You can name it whatever you want. I called it Toluca to be descriptive. And so this reads the data from this file into the object and stores it as a data frame in Toluca. A key detail that I want to point out, though, is that R has to know exactly where the file is located. So the first thing I did was I set my working directory. The working directory is really where R is going to look for any data or any information that you want to provide with R. So the data is in this folder on my computer. So it's in my Dropbox folder, in the UCD files folder, in the teaching folder, and the folder for this class, under data, under chapter 1 data sets. So it's a pretty long file path. You can place yours on the desktop and shorten up the way that you're going to access your working directory. The big picture here is that I have to tell it what directory to look in, and then I tell it what file I want to read in. When I read it in, the file is going to have the two different variables. So actually, let's just read that in. So I highlight that and I hit Control R on my Windows computer, and then I type Toluca. Oops. I type Toluca in the terminal window here, and that shows me the data that was read in. But this is not very descriptive. V1 and V2 stand for variable 1 and variable 2. That doesn't tell me what they are, and so I can actually name the two different variables in my data frame. So I'm going to name them lot and hours. So the first column is going to be the lot size, and the second column is going to be the number of hours needed to produce that lot. And a convenient command, which makes the data easier to work with, is the attach command. So if I use the command attach Toluca, what it does is it allows me to reference the first column using the word lot, and the second column using the word hours. And you're probably not going to get this. I only got this simply because I've already attached this data set once and it's kind of mad at me. So when you do this, you won't see this, but that doesn't mean that it's not working incorrectly. So we attach Toluca, and that allows us to simply write lot or hours to access those two different variables. So it's always helpful when you're doing regression to plot the actual data you're looking at. So we're going to use the plot function. That's the workhorse function for creating plots in R. And you give it first the x variable and then the y variable that you want. And if you want to relabel the x and y axes, you just do xlab, x label is equal to, and then in quote put the string that you want to use. And we can do the same thing for the y-axis using ylab. So this will create a plot of the number of hours worked versus lot size, and then we have named the x and y axes accordingly. So we can see that there's an upward linear trend in the data here. The data looks like it can be fit pretty well to a straight line. So let's estimate beta 1 and beta naught using their least squares estimates. And so this is our notation right here. You don't have to worry too much about what this means, but just to kind of walk through what it does stand for. So what I'm going to do here is, in order to make the analysis simpler, I'm going to take the hours variable that's in Toluca, I'm going to store it as the variable y, and I'm going to take the lot variable that's in Toluca and I'm going to store it as the variable x. So I'm only doing this to make things in shorthand, so I don't have to type out the names, so the names aren't as long when I'm typing it out. So in order to estimate beta 1, I take each of the x's and I multiply them by the y's, I add them all together. So this is a sum of x sub I, y sub I. And I subtract from that 1 over n times the sum of the x's times the sum of the y's. Okay, so this is the numerator of my least squares estimator for beta 1. And then the denominator, I have to take each of the x values and I square them, then I add them all together. Then I subtract from that the sum of the x's squared divided by 1 over the sample size. So the number of observations is 25, which is where 1 over 25 is coming from. And when I do that, I get my least squares estimate of beta 1, which in this case is going to be 3.57, which is the same value that we already saw on the slides. To calculate beta naught hat, the least squares estimate of beta naught, I simply take the sample mean of the y's, and I subtract from that the sample mean of the x's multiplied by the least squares estimate for beta 1. And so that's what I'm going to do using this command right here. And b naught is equal to 62.37. So these are the same values that we already saw in the lecture slides. You might be saying to yourself, it sure seems like there should be an easier way of doing this. It would be really, even though it's a lot easier than doing it by hand, it would be really annoying to have to do this every single time you want to find the least squares estimates of beta naught and beta 1. And so R is a statistical software package, so it has lots of nice functions to do common statistical analysis. And so this is the simple way of doing it. in R. So the function that we're really going to use primarily in this class is the LM function, which stands for linear model. And so with our linear model function, what we're going to do first is provide it with the response variable, which in this case is hours. And then we have this tilde symbol, which means regressed on. So the response is regressed on all of the predictor variables on the right side of the equation. So we want to regress the hours variable on lot size. So we have hours tilde lot, which means that we have just a single response regressed on the single predictor variable. And when you have data stored in a data frame, you can provide that data using the data argument of your function. So the first thing we do here is we tell it what function we want to, we describe the regression relationship, and then we provide the data set that these variables are stored in, and they're stored in the Ch01 data set that we read in earlier. So I use the linear model function, and R is going to do its thing. It's going to find the least squares estimates, and I'm going to store the information. The LM function provides in an object called myLM. And if I look at myLM, you can see that it provides me with the two estimated regression coefficients. The intercept, beta naught hat, is 62.37, and the estimated slope is 3.57. And this is the same information I would get if I simply typed LM of y tilde x, because I have stored the data contained in hours in the variable y, and I've stored the lot variable in the variable x. So that's using the built-in function that R provides in order to find the least squares estimates of beta naught and beta 1, which I'd say that's a lot easier than writing out a formula of this nature in R. So I have my least squares estimates, and oftentimes after you find your least squares estimates, a nice thing to do is to plot the estimated regression function. And there are various ways of doing that, but when you're doing simple linear regression, the easiest way to do that is using the AB line function. So the name for this comes from the old algebraic expression y equals a plus bx. So the idea is that you provide it with the intercept, you provide it with the slope, and it's going to draw a straight line on your data set for that line. So if we do AB line myLM, then what R does is it draws the estimated regression relationship on the plot that we've already created. I will point out that if you've already closed your plot and you try to use the AB line function, it's going to be mad at you. So it only draws this line on a plot that's already been created. So let's recreate our plot. And then the AB line function easily draws the estimated regression function on our data set. So we now have the estimated regression relationship drawn on the data, and as we can see, it fits actually pretty well. So let's talk about estimating the mean response. So a value of the response variable is simply called a response. Okay, at least that's the terminology that I like to use. And the way that we denote the mean response, the average response for a specific value, is the E of y, so the expected value of y. And the mean response is the mean of the probability distribution of y corresponding to the level x of the predictor variable. And the Gauss-Markov theorem can be used to show that the y hat, the estimated value of the estimated regression function, is an unbiased estimator of the mean value of y, and also has the minimum variance among all unbiased linear estimators. So in other words, if you want to estimate the mean response, the best estimator that you can get is simply to use the regression function and then to plug in the value of x that you're interested in estimating the mean for. So with that, we have some terminology that we should use. So the ith fitted value, y hat of I, is equal to beta naught plus beta 1 hat x sub I for I equals 1 to n. So these are the estimated mean responses for y hat of I is the estimated mean response for the ith response. So for the ith value of x, we plug that into our estimated regression function, and that gives us our ith fitted value. And notice that this is not the same thing as the ith observed value. So the observed value is y sub I. The ith fitted value the value we obtain when we plot x sub I into the estimated regression function is denoted y hat sub I. So related to the ith fitted value is the fitted line y hat equals beta naught plus beta 1 hat x. So this is just the estimated regression function, which is a little bit more general, and to get the ith fitted value, we simply plug the ith value of x into this equation right here. And related to that is the ith residual, which we'll denote by e sub I. So the ith residual e sub I is y sub I minus y hat of I. In other words, it's the deviance, or the difference, between the observed response and the estimated mean response. So the ith fitted value is the estimated mean for the ith observation. We subtract that from our ith response to obtain the ith residual. And if you're kind of wondering exactly what these are, let's draw a picture of this. So let's say we have some data similar to the data that we have already been working with. So we'll have 4 observations there. And let's say that we have our estimated regression function, y hat, which is beta naught hat plus beta 1 hat x. And if this is the first observation here, that's x1. And the way that we get the first fitted value is by taking x1, plugging it into this equation right here, and that is going to give us the value on the estimated regression function basically if we draw a vertical line if we draw a vertical line from x1 up to the estimated regression function, the place where they intersect, that is going to be the fitted value for that particular observation. Okay, so the first fitted value in this example right here is just the value where the location on the vertical axis where the estimated regression function and the vertical line going from the first value of the predictive variable intersect. So we have our estimated regression function, we have our first fitted value, and the residual is going to be the vertical distance between the actual response and the estimated mean response. So just continue that to try to make things clear. So if this is the second observation, then x2, the value of the second predictive variable, is right there. And if I draw my vertical line up from x2, that intersects the estimated regression function right there. So that is the value of y2 hat. And the vertical distance between the observed response for the second observation, y2, and the difference between the response for the second observation and the estimated mean for the second observation is E2. So we have that vertical distance is the second residual. Then you can proceed to denote the remaining third and fourth observations. So visually, that's what these things are doing. So the estimated regression function here is the estimated regression equation. When we draw vertical lines from each of the values of the predictive variables up toward the regression line, the place where they intersect the estimated regression function, that vertical location is going to be the fitted value for that particular observation. And if we find the vertical distance between each observation and the ith fitted value, that's going to give us our residuals. So let's talk about some properties of our estimated regression line. The first property is that the least squares, if you sum the residuals, if you sum the if you sum the least squares residuals, then their sum is always going to be equal to 0. Doesn't matter what the data set is like, doesn't matter about any additional piece of information, the sum of the least squares residuals is going to be 0. Another fact about the least squares estimates, or about the least squares line, is that the sum of the squared residuals is the minimum for all possible regression lines. And that's why this is called the least squares estimators, the least squares lines, because these are the estimators of beta naught and beta 1 that minimize the sum of the squared residuals. And as if we remember, the whole reason that we chose these estimators were because they minimized the least squares criterion Q, which is really just this point number 2. And a third point is that the fitted line always goes through the point x bar, y bar. So it doesn't matter, once again, what the data set is like, the least squares line, the estimated regression line obtained using the least squares error criterion, is going to always go through x bar, y bar. So just to kind of show you what it might look like to prove the first property of the estimated regression line, we are going to look at a brief proof of that. So let's show that the sum of the residuals is equal to 0. So we want to show that the sum of the residuals is equal to 0. And so what we're going to do is we're going to expand out the residuals. So the sum of the residuals is equal to each observation minus the ith fitted value. Okay, so the definition of the ith residual is that it's the ith observation minus the ith fitted value. And we also know that the ith fitted value is obtained as beta naught hat plus beta 1 hat x sub I. Alright, so I'm simply replacing the formula for the ith fitted value into this equation right here. And now I'm going to expand this equation so I get the sum of the y's minus in beta naught hats minus beta 1 hat times the sum of the x's. And so re-expressing that or reorganizing that, I get the sum of the y's minus beta 1 hat times the sum of the x's minus in beta naught hat. And so now I'm just going to look at this term right here, and I'm actually going to expand that out over here on the side. So beta naught hat, the formula for beta naught hat is y bar minus beta 1 hat x bar. And recalling that y bar is simply the sum of the y's over n, if we multiply y bar by n, I'm simply left with the sum in the numerator. So this is equal to the sum of the y's minus beta 1 hat, and if I multiply n by x bar, I have a similar property. So I get beta 1 hat times the sum of the x's. And so I have re-expressed in beta naught hat as the sum of the y's minus beta 1 hat times the sum of the x's. And so if I substitute that information into this equation over here, I get minus the sum of the y's minus beta 1 hat, the sum of the x's, and it's pretty obvious now that these cancel each other out, and we get 0. So the sum of the least squares residuals is always equal to 0, regardless of the data set under consideration. So another parameter that we often need to estimate, or in practice always need to estimate when we're doing simple linear regression, is the error variance sigma squared. So we know that the errors in our simple linear regression model have mean 0 and variance sigma squared. And just to sort of motivate the way that we estimate this parameter, recall that if we just had n IID observations, so n observations drawn from a population, drawn randomly from a population, that have and each observation has mean mu and variance sigma squared, then the estimator for sigma squared, the estimator for the variance, is just the sample variance, which is the sum of the square difference between each observation and the sample mean, divided by the degrees of freedom of n minus 1. So this is the standard formula for the sample variance. If you don't remember it, you may want to go back and look through your old statistics book. But this is just the standard formula for the sample variance. So we take the sum of the squared difference between each observation and the estimated mean divided by the degrees of freedom. And degrees of freedom is something that is frequently misunderstood, and so just to try to give a hopefully helpful but very brief description of what it is, it's really just the number of independent observations in a sample that may be used to estimate a parameter. And typically the degrees of freedom of a parameter estimate is the number of observations minus the number of parameters that one needs to estimate along the way. And so when we were looking at the degrees of freedom for the sample variance, the only parameter that we had to estimate was mu, which was estimated by y bar. So the number of degrees of freedom is n minus 1. Well, on the linear regression model, the sum of the square deviations from the estimated mean is denoted by SSE, where SSE stands for the error sum of squares, or the residual sum of squares, since this difference is just the residual right there. So SSE is the sum of the square deviations between each response and the estimated mean y hat sub I. And the degrees of freedom for the error sum of squares is going to be n minus 2, because in order to get this sum, we had to estimate both beta naught and beta 1 hat along the way. Because remember, y hat sub I is equal to beta naught hat plus beta 1 hat x sub I. So in order to get the estimated mean for the ith observation, we have to estimate both beta naught and beta 1. And so this sum has n minus 2 degrees of freedom. And consequently, the estimator for sigma squared in a linear regression model is going to be also denoted as squared. And it's often denoted by MSE, the mean squared error, which is the error sum of squares divided by n minus 2, the degrees of freedom for the error sum of squares, which can be re-expressed as the sum of the square deviation between each response and the ith fit and its associated fitted value divided by n minus 2, which can be re-expressed as the sum of the squared residuals over n minus 2. Okay, so MSE stands for error mean squared with the residual mean squared, and we won't show it, but the mean square error is an unbiased estimator of sigma squared. In other words, the expected value of the MSE is equal to sigma squared. And typically, if you want to estimate sigma, the typical estimator is just simply denoted S, which is the square root of MSE. So you can see that we have S squared is equal to MSE, and that's our estimator of sigma squared. So if we want to estimate sigma, we simply take the square root of all of those things and get S equal to the square root of MSE. So that's our least squares estimator of sigma squared and sigma. So going back to R, let us look at how we get some additional information related to the other parameters of interest. Alright, so we've already fit our linear model, so I haven't closed this out or anything, so all the information I had before is still present in R. And so in order to determine the error sum of squares or the residual sums of squares, the first thing I have to do is I need to calculate my fitted values. So there are a couple ways of doing that. So one is I can take my least squares estimates of beta naught and beta 1, and I can put them in the right formula and calculate those manually in R. Okay, but as you might expect, R tries to make our life a little bit easier. So if you want the fitted values, that's actually stored in the mylm object that we saved earlier. Okay, so remember, I took my linear model object and I stored it in mylm. So if I do mylm $fit, that's also going to give me the fitted values for each of the observations. And when I have my fitted values, I can use those to obtain my residuals. So if I take my responses y and I subtract off my fitted values, I can get my residuals, which are shown right here. However, there are simpler ways of doing this in R instead of calculating it manually. So if I take my mylm object, my linear model object I've already saved, and I do $resid, that will also provide me with the residuals. Or I can use the residuals function on mylm, and that will also provide me with residuals. And one thing you might check here is that if we sum the residuals, we should get 0 or something numerically close to 0. And so you can see here that we get negative 2.9 times 10 to the negative 14 power. So there's going to be some numerical error when we do these computations, but this, for all intents and purposes, is 0. So the sum of the residuals is equal to 0. So that's how we obtain the fitted values and residuals directly in R. In order to calculate the error sum of squares, we can take the residuals, square them, and then add them together, which I show both here and right here. Unfortunately, there's no straightforward way to get the error sum of squares. All it takes a few steps. So that's the error sum of squares right there. And if you want to determine the MSE, then I can take my error sum of squares and divide by the degrees of freedom, which, if you remember, there are 25 observations, and if I subtract off 2, I get 23. So the mean square error is going to be 2,383.716, or a more productive way of doing that. If I didn't know the number of observations, I can ask R how many observations are in the hours variable, and that will return 25. And so I can just put that in this expression right here, and I get the same value. Or if you want to obtain the mean square error most efficiently in R, you use the summary function on the linear model, on the stored linear model. Use the $ symbol, and then access the sigma variable that's stored in that object. Then we square it. So this right here will give me sigma hat, essentially, or S. This gives me the square root of MSE. And so if I want the MSE, I have to square it. So my mean square error is 2,383.716. And if you use the ANOVA function on your linear model, then you'll see that this is going to produce pretty much all the same information in a slightly different format. So we have our error sum of squares, we have our mean square right here, and this may not look the same, but the reason is because R is not showing all the decimal places. So if I increase the number of digits in R to 10, and then look at the output, you'll see that it looks closer to what we've already obtained. Okay, so basically what we've done right now is we've learned how to obtain the fitted values in R, the residuals in R, and then calculate both the error sums of squares, the MSE, and look at the ANOVA table, which we'll talk more about that in subsequent chapters. So we've talked about these different estimators, and the Gauss-Markov theorem tells us that the least squares estimators of beta naught and beta 1 are the minimum variance unbiased estimators among all unbiased linear estimators. But in order to construct interval estimates and perform hypothesis tests, in other words, to construct confidence intervals and do hypothesis tests for these parameters, we're going to have to make some additional assumptions about the distribution of the error terms specifically. So up to this point, we have not assumed a distribution for the errors. We only assumed that they had mean zero, variance sigma squared, and that they were independent of one another. But the normal error regression model is going to be the same model that we fit before, with the additional assumption that the errors have a normal distribution. So if you compare this slide to the slide near the beginning of this chapter, you'll see that all the assumptions are the same, except that I've added the additional assumption that the errors are normal, which is why this is called the normal error regression model. So we already had that the errors had mean zero, constant variance sigma squared, they were independent, but now I'm making the assumption that they're all normal, which means that they are IID normal 0 sigma squared. So as I mentioned before, this is the same model as before, except that we have specified that the distribution of the errors is normal. Since the errors are normal and uncorrelated, this implies that they're independent. And the normal error regression model implies that the y's are also independent, with mean given by beta naught plus beta 1 xi, and a constant variance of sigma squared. So we've already talked about how to estimate these parameters using the least squares error criterion, but you can additionally estimate these parameters using the method of maximum likelihood. So we're not going to talk in a lot of detail about this method. This was talked about. You can learn more about this in the statistics class, Math 4820, and the notes are available on Blackboard if you want to do so. But essentially what you do, or I guess the motivation behind maximum likelihood, is that you want to estimate your parameters using the values that maximize something called the likelihood function of your data. And practically what this means is that these are the estimators which are most likely to have generated the observed data. So we ask ourselves, what data did we see, and what values of the parameters are most likely to have produced this particular data set. And another way of thinking about this is that if you actually plotted the likelihood function, then the values of the estimators would be the modes of your likelihood function. So the values that are the largest values of your likelihood function. And the likelihood function of a set of observations is simply the joint density function of the observed data. And we often denote the likelihood function by L for likelihood, and it's a function of the parameters. So you have to go back and look at the notes from statistics if you want to remember what a density is, or if you don't remember what the density is. But the density for a normal observation looks like this right here, with this being the variance and this being the mean. And since our observations have a mean given by beta naught plus beta 1 xi and a constant variance of sigma squared, the marginal density of each observation is expressed using this formula right here. And because our observations are independent, the joint density is simply the product of all the marginal densities. So if we take the marginal density for each observation and we multiply them all together, that's going to give us our joint likelihood function as a function of beta naught, beta 1, and sigma squared. And so that can be re-expressed somewhat more simply using this formula right here. And though I'm not going to derive it, if you actually go about finding the maximum likelihood estimators of beta naught and beta 1, which basically means you look at this function, you take the partial derivative with respect to beta naught, you set it equal to 0 and you solve for beta naught, and then you also take the partial derivative with respect to beta 1, set it equal to 0, and then solve for beta 1, you'll actually find that you get the exact same estimators as the least squares estimators. So the maximum likelihood estimators of beta naught and beta 1 are the exact same as the least squares estimators. On the other hand, if you use this formula to find the least squares estimator of sigma squared, so we take the derivative of this function with respect to sigma squared, set it equal to 0, and solve for sigma squared, we'll see that the maximum likelihood estimator of sigma squared is going to be the error sum of squares divided by n. Whereas if you remember before, the formula was the error sums of squares divided by n minus 2. And because the previous estimator was unbiased, this means that the maximum likelihood estimator of sigma squared must be biased. That doesn't necessarily mean that's worse, it just depends on what you're interested in, but the maximum likelihood estimator of sigma squared is going to be biased in a simple linear regression model. And as I mentioned, I'm not going to derive these for you, but if you look on page 32 of your book, you can find the derivations of these estimators for yourself. Okay, so let's just wrap everything up here. So essentially what we've talked about is we've talked about the simple linear regression model. We've talked about how to estimate each of the parameters, how to interpret the parameters, how to estimate the error variance, and we did an example involving Toluca data. Now let's do another example just to try to wrap things up and bring everything together. So the director of admission of a small college selected 120 students at random from the new freshman class in an effort to determine whether a student's grade point average at the end of their freshman year could be predicted using their ACT test score that they used to get into the college. So here's a plot of the ACT scores versus grade point average. And this relationship doesn't follow a straight line as closely as our previous example, but we still might be able to gain some information by fitting a simple linear regression model to this particular data set. And so I'm going to go into R actually, and I've done this exercise, we've done this example in R, so we'll just walk through the information in this example. So as in the previous example we've done, the first thing I have to do is tell R where my data is located. So it's in this folder on my computer. And then once I specify the folder where my data is located, I use the read.table function to read the data, and I store it as a data frame in an object called college. By default, college doesn't have any names for the variables, just V1 and V2. So I name the variables in college. I'm going to name it GPA and ACT for the GPA and the ACT score. And then I'm going to attach that data set so that I don't need to, so I can simplify some of my so I can simplify some of the later commands. So the plot, or the command used to plot or create the plot that I showed in the lecture slides, is just this plot function right here. I specify the x variable, I specify the y variable, and then I label the x and y axes. And in order to obtain my least squares estimators of beta 0 and beta 1, I use the lm function, and I'm going to store that object in my lm. And the reason I put these parentheses around it is that that will display the result to the screen. Whereas if I just did my lm without the parentheses, it would simply store the information in my lm. So these parentheses on the outside edges tell R to actually display the information from the lm command to R. So you can see that we have our estimated intercept and our estimated slope. And if I want to add that line to my observed data plot, I simply use the AB line function. So I run that using the Control R command, and there's our least squares line plotted on the observed data. As you can see, it somewhat describes the relationship, though this relationship is not nearly as nice as in the previous data example. And if I wanted to estimate the mean response when ACT score is equal to 30, so the administrator says, well, if the person has an ACT score of 30, what's the average GPA I can expect to see at the end of their freshman year? What we need to do then is we simply plug 30 into our estimated regression function, which I've done right here. And so I can just use R as a calculator to calculate that. Or a better way of doing it, though it's a little more complicated, is to use the predict function. So the predict function takes the linear model object, which I've called my LM, then I have to specify the data value I want to use to make my prediction. In this case, the new data I want to make a prediction at is when ACT is equal to 30. So I have to create a data frame, which we haven't talked about this yet. This is just showing you how we're going to do these things. I create a data frame object, and I specify the name of the variable as ACT, the same name as in my linear model object. And I specify a value of 30, and I provide that as new data, and then R will automatically predict the mean to be 3.28, just like we saw when we calculated it manually. And if I want to determine the mean squared error, then I simply use the summary function myLM. I access the sigma variable in the summary object and square it. And so my MSE is going to be 0.3882. And if I want to look at some of the additional information, I can do that using the ANOVA function. So that gives me some more of the information. So looking at our output and trying to summarize it or interpret the results, the estimated fitted line, the estimated regression function, is y hat equals 2.11405 plus 0.038883 or 0.03883 ACT. So this is my estimated intercept and this is my estimated slope. And if we want to interpret those two parameters, it means that the estimated mean GPA when a student's ACT score is 0 is 2.11. So when ACT score is equal to 0, the average GPA is 2.11. Of course, this doesn't make any sense whatsoever. And the reason for that is that we're badly extrapolating. The smallest ACT score we actually saw in the data was 15, which is nowhere near 0, which is why even though that interpretation is mathematically correct, it's not sensible. Doesn't make any sense. On the other hand, the interpretation of the slope parameter, beta 1 hat, is that the estimated increase in GPA is 0.04 per 1 unit increase in ACT score on average. In other words, if we look at a student who has a certain ACT score, and then we increase the ACT score by 1, the average GPA, the expected GPA at the end of their freshman year is going to be about 0.04 points higher than it would if they had an ACT score 1 point lower. And then as I mentioned here, so we've already done this actually, if I wanted to estimate the mean GPA for a student with an ACT score of 30, the estimated mean would be obtained by simply plugging 30 into our estimated regression function and doing the calculation. We get 3.28, and the estimated variance is s squared equal to 0.0388. So this is really just an introduction to the simple linear regression model. In terms of knowing R and understanding all that we did, don't worry about that right now. On Tuesday of next week, we're going to actually go through a crash course in R. So I'll teach you more about R so that you understand exactly what I did in the background. And the big picture here is you want to understand what the simple linear regression model is. You want to understand the interpretation of the parameters. You want to understand what each of the different terms are, what y sub I is, what epsilon I is. You want to understand the distributional assumptions. We talked about how to estimate the regression parameters using least squares estimation, understand what we're doing there. And then using the least squares estimates, we were able to obtain the fitted values, which is the estimated mean response for each observation, the fitted line or the estimated regression function, same thing, which is really just the regression equation replaced where the parameters are replaced by the estimated values. And from those we can obtain the residuals, which is the vertical difference between each observation and the estimated regression line. And then that allowed us to obtain estimates of the variance, right, which is simply the MSE divided by the degree, or the MSE, which is the error sum of squares divided by n minus 2. And if we make the additional assumption that the errors are normal, then that will allow us to make some additional statistical inference. It allows us to construct confidence intervals and do hypothesis tests for the parameters of interest. We won't talk about that until chapter 2. Thank you for taking the time to listen to this lecture. If you guys have any questions before next Tuesday, please give me a call or send me an email, and I'd be happy to answer your question as quickly as possible. Have a great day.